Automatic control of central systems. Part 3. Automatic control of central systems will be explained. In Part 3, the following items will be explained in detail. Chilled water storage system. Internal melting ice on coil thermal storage system. External melting ice on coil thermal storage system. Chilled water storage system will be explained. Chilled water storage system has primary a chilled water source consisting of a chiller, a primary chilled water pump, a cooling tower and a condenser water pump. The open-type storage tank stores the thermal of chilled water generated by the primary chilled water source. Chilled water is supplied by multiple secondary chilled water pumps on the load side. The drawing shown on this slide is an example of a system where two chillers are used on the primary chilled water source side, while some cooling coils for the air conditioner are flow controlled by the two-way valve on the load side. In addition, two secondary chilled water pumps are used to supply chilled water on the load side. The automatic control system includes the following components. The temperature sensors TE1 and TE2 to control the chilled water outlet temperature of the chiller. The temperature indicating controllers TIC1 and TIC2. The temperature control valves TCV1, TCV2, TCV3, and TCV4. The temperature sensors TE3, TE4, TE5 and TE6 to measure the temperature inside the storage tank, the electromagnetic flow meter SM1 to measure chilled water load flow rates, the unit number controller used to determine the number of chillers based on thermal storage capacity, the pressure sensor PE1 to control supply water pressure of the secondary chilled water pump, and the pressure indicating controller PIC1, and the pressure control valve PCV1. Installation of chilled water storage tank in the system can reduce the capacity or unit number of chillers. In addition, the temperature of the chiller inlet can be set higher than that of the primary and secondary pump systems to increase the temperature difference. As a result, the efficiency of system operation improves. Now, how the system operates will be explained. The unit number of the primary chilled water source is controlled based on excess and efficiency obtained from comparison of the thermal storage capacity of the chilled water storage tank and the target thermal storage capacity for the corresponding time of day. The thermal storage capacity is calculated by multiplying respective four temperatures measured by four temperature sensors TE3, TE4, TE5, and TE6 by the respective areas or flow rates covered by the corresponding sensors. The temperature sensors TE3 to TE6 are arranged in order from the low temperature side to the high temperature side, which accumulates the heat radiated by the cooling coil. The number of the temperature sensors is generally 2 to 8 depending on the areas of the chilled water storage tank. Target thermal storage capacities are set once every hour. The graph on this slide is an example of target thermal storage capacities. Target thermal storage capacities are set higher during hours. At night, when electricity charges are inexpensive, the thermal storage capacity is fully accumulated by 8 a.m. when air conditioning is started. The thermal storage capacity is consumed up to the lower limit, 20 to 30% at the end of air conditioning to prepare for the start of charging storage. Between 12 p.m. and 2 p.m. when the cooling load reaches its peak, the target thermal storage capacity is set lower to limit the operation of chillers. Next, temperature control of the outlet of chillers will be explained. The outlet of the pipelines for chillers are controlled to prevent the chilled water at a high temperature, higher than the set temperature of the outlet of the pipeline for chillers, which hasn't been completely chilled. For example, at the startup of chillers, from flowing into the low temperature side of the chilled water storage tank. If the temperature of the outlet of the pipeline for chillers is equal to or higher than the set value, the temperature of the outlet for chilled water is maintained at the set temperature of the inlet of the pipeline for chillers by mixing the chilled water from the low temperature side with the chilled water from the high temperature side for absorption. In addition, when the primary chilled water pump is stopped, PI calculation of the temperature indicating controller of the corresponding system stops, and the chiller inlet temperature control valve completely closes. Next, the secondary chilled water pump will be explained. The secondary chilled water pump is started at the startup of the air conditioning system. After startup forced operation, the secondary chilled water pump starts unit number control based on the chilled water load flow rate, which has been time averaged during the start-stop determination interval. The increment percentage to increase the number of secondary chilled water pumps in operation from 1 to 2 is approximately 100 to 105% of the rated capacity of one secondary chilled water pump. Set the on-off differential, that is, the difference between the increment percentage and the decrement percentage, to reduce the number of secondary chilled water pumps from 2 to 1. Considering the 10 to 15% of the rated capacity as a rough indication. The flow rate used for unit number control determination for secondary chilled water pumps is a flow rate for 3 to 10 minutes, and the time average value is used. The number of secondary chilled water pumps to be controlled is determined after the average load end period of 3 to 10 minutes. The operating sequence of secondary chilled water pumps to be operated and stopped through unit number control are rotated in order to maintain an almost equal operating time between the two secondary chilled water pumps. If a secondary chilled water pump has trouble, it is removed from unit number control. New startup and stop directions are not output to it. The characteristics of the startup forced operation period, the increment percentage, the on-off differential, and the start-stop determination interval properties are different depending on the type of pumps and air conditioning systems. It is necessary to review them based on the client's buildings. The number of secondary chilled water pumps is controlled based on the time averaged load flow rate during the start-stop determination interval. However, for example, if an operating pump has trouble and fails to operate as stipulated, or if the load has dramatically changed, the system carries out unit number increment or decrement correction of pumps based on supply water pressure. First, unit decrement correction with the supply water pressure sensor PE1 to reduce the number of the secondary chilled water pumps to be operated will be explained. When two secondary chilled water pumps are in operation, If the supplied chilled water pressure measured by the pressure sensor PE1 remains equal to or rises above the upper limit of the unit decrement set pressure for the fixed period, the number of secondary chilled water pumps to be operated is reduced by 1. If unit decrement is requested, the number of secondary chilled water pumps to be operated is reduced, even during the start-stop determination interval. The pressure for unit decrement is said to be the pump rated pressure or higher based on the pump capacity curve. Unit decrement based on supply water pressure prevents excessive increase in supply water pressure due to a suddenly reduced load. Next, unit increment correction based on supply water pressure will be explained. If an operating pump has a problem and cannot operate as stipulated, the supply water pressure drops. When one secondary chilled water pump is in operation, if the supply water pressure remains equal to or drops below the pressure set for unit increment for the fixed period, unit increment request is issued to activate the inactive secondary chilled water pump. If unit increment is requested, the number
Under
of
the
secondary chilled water pumps to be operated for air conditioning during the start-stop determination interval.
Of heat load
The pressure
calculation.
for unit increment is said to be the pump rated pressure or lower based on the pump capacity curve. The contents I will explain are shown on this slide. Next, supply water pressure control will be explained. If you plan and design air conditioning system by the inverter installed
it is
on the
basic to
secondary
know
chilled
heat load for
water
air
pump to
conditioning.
control the number of
For air
rotations
conditioning
of the pump
load,
motor and
the
by
heat
the
load
pressure
to be
control
taken into
valve
account or
PCV
air
one
conditioning
installed
cooling
between the
load
outlet
and air
and
conditioning
inlet
heating
pipe
load.
connected to the pump. Air conditioning
Cooling
supplied
load
chilled
include
water
cooling
pressure
load
is
and
detected by the
dehumidification
pressure
load.
sensor PE1.
Heating load
The
include
number
air
of
conditioning
rotations
heating
is
load and
controlled by the
humidification
pressure
load.
indicating controller
After
PIC
calculating
and
the
such
inverter
variable
load,
installed on
we
the
will
chilled
determine
water
the device
secondary
capacities of air
If the
conditioners
pressure
and
is
heat
beyond the set
facility.
value, the number of rotations of pump motors in operation is respectively reduced.
Generally, heat load.
The number of
There are various
rotations of two
categories.
pump motors is
That
reduced
is,
and adjusted
thermal
to be
room
the
load,
same.
system
Each
load,
pump has a
heat
minimum
source
motor
load and
rotation number to
the
secure a
heat
minimum flow
extraction
rate.
and heating
If the
capacity to be
pressure
kept at a
increases while
constant
each pump
temperature
motor
and
is
relative
rotating at the
humidity in a
minimum
room are
rotation
called
number,
thermal room
the
load.
pressure is controlled
Thermal
by
room load
opening the
includes
pressure
heat gains
control
or
valve
heat losses and
PCV1.
storage heat load
The
for
rated flow
buildings.
rate of the pressure
Let's
control
think of
valve
heat
used
load
under
caused by
inverter control
cooling.
is often
The
selected
solar
based on
energy
30 to
flows
40%
into rooms
of the
through
rated
window
capacity
panes.
per pump. If you consider
If
the
you
moment
select
when
the
it
rated
flows
flow
in,
rate
and
the
the
load
pressure
caused by
control
the
valve
energy is
based on the
equal
rated
to the heat
capacity
gain.
per pump.
However,
If the pressure
all
is
of the
controlled
energy
by
does
the
not
pressure
always
bypass
act as load in
valve,
the room.
and if you cancel
Some of it
inverters,
is
you
absorbed
may
into
reduce
and
the initial
accumulated in the
cost.
building construction
When all
framework.
secondary chilled water
After
pumps
some
stop,
delay,
PI
another part of
calculation
it
by the
acts as
pressure
room heat
indicating
load.
controller
For
PIC1 can
intermittent
be
air
stopped.
conditioning, room
As a
temperature
result,
changes.
enhancement
If
of
air
integral
conditioners
control
are turned
caused by
off,
the difference between
pick
the
up
PV
load and
value
pull
and the
down
setting
load are
value
added to
is
the heat
prevented.
load when the air
Conditioners
conditioners are
calculation
restarted.
is carried out while the
This
pump
time,
is stopped.
we will
The pressure
determine heat
bypass
gains and
valve
heat
remains
losses.
completely closed
In
for a
addition,
while.
how
As
system
a
load
result,
and heat
supply
source
water
loads are
pressure
related to
cannot be
heat loads
controlled.
as shown on this slide. A
Next,
drawing
the
showing a room
internal
heat gain to
melting
be
ice
cooled is
on
shown
coil
on this
thermal storage
slide.
system will be
The heat
explained.
from the sun enters the room through walls. The heat comes in from outer wall
Ice
portions
thermal storage
including
systems
roofs
are
and
roughly
windows facing the
classified into
outdoor
two
air.
types.
Such
Static
heat is
type,
one element
ice
of the
on
heat
coil,
transfer
and
load.
dynamic type.
The solar
Ice
energy from the
harvester.
sun comes into the
Internal
room through
and
the window
external melt
panes.
ice on coil
This
belong
is
to
the
the
solar
static
load.
type group. In the room,
The static
body temperature is higher than the room temperature, so the heat generated by a person also acts as a heat load. The dynamic type in addition, heat is generated by lighting equipment and also intermittently feeding the ice generated by air coming in through the gaps in the sash of the window and the door at the entrance may also cause loads. The mixture of liquid and subtle ice loads. Lighting load. Here, equipment static type ice thermal storage system will be respectively. The internal conditioning on the temperature of the ground is lower than the room temperature is melted. Therefore, the heat escapes from the inside of the floor in the basement walls not shown in the drawing. The slide is an example of heat is a factor in causing a chilled water pump, a brine chiller, a brine water heat exchanger. Air conditioning load for buildings includes heat transfer load and thermal storage tank. The heat is the automatic control system includes the following heat transfer, heat convection and heat radiation to detect the temperature and energy penetrates objects. The water level glass window and comes into the room to detect the water level is reflected away, and some of it is directly absorbed in the construction framework based on the thermal storage capacity. The solar energy is absorbed into the room by heat transfer. TCV3. The heat conveyed by heat transfer and the radiation heat absorbed directly into construction frameworks are conveyed into the room by heat convection. The thermal detector to control the temperature of the outlet of the heat transfer load and solar heat load temperature indicating controller. Calculate air conditioning cooling load based on the direction of the walls and windows and specific time interval. Water pump CP1 under air conditioning. The temperature of the ground is lower than the room temperature. Bypass valve. The heat is escaping through the earth's floor in the basement walls not shown in the drawing is a factor in the internal melt ice on the escape heat system will be for the room during air conditioning. So it is not considered as a heat load operating the brine chiller will be explained. However, it is considered as a heat load opening and during heating in winter. However, the solar energy as shown in the table on the slide. So it is considered as a heat load. It is formed by the brine chiller and tube pipe and the ice thermal storage load generated in the room includes people load. Lighting the brine water and equipment heat separated from the circuit. Those load are factors in heat gain. If the chilled water pump is consider them only cooling load cannot be sent to cooling people load includes sensible heat load caused by heat generated by people and latent heat load deficiency obtained from comparison of the thermal storage capacity of the ice thermal storage tank and the target operation and room temperature for the corresponding the combined heat of sensible heat and latent capacity on the type of work, but it remains the same in the room temperature sensor to if the room temperature rises, the latent heat also rises due to the increase of sweat. Sensor LE1 based on the type and wattage of lighting equipment, determine the lighting load, discharge mode to melt ice generally, and send chilled water to the secondary load and air conditioning equipment are only sensible heat load. During discharge you should however notice that latent loads may occur for the brine water heat exchanger or switch where cooking in the table on the slide produce steam. As a result, if you calculate the heat generated by manufacturing equipment and the consider factors including the electric capacity and the operating ratio of the device. The chiller is separated from the circuit. The chilled water pump determine the heat transfer load water to the load side. Determine the coefficient of overall heat transfer based on the characteristics and thicknesses of the material of the heat exchanger for chilled water and by determine the heat transfer load of the construction framework by using the result. Meanwhile, The
A method to determine the coefficient of overall heat transfer factor is shown on the slide. You can determine the heat transfer load of the construction framework by using the determined coefficient of overall heat transfer factor. The square area of the target portions and the temperature difference of delta T. The ice thermal the temperature difference delta T is used around the tube pipe is uniformly melted. It is used when the heat transfer load caused by outer walls is considered during air conditioning. Use the equivalent temperature difference. Effects of the sunlight and related to the heat accumulation are also considered. Otherwise, use the temperature difference between that of the outdoors or the next room and that of the target room. If the next room is not air conditioned, in general, the temperature between the outdoor temperature and the indoor temperature should be considered the temperature of rotations of the pump impeller is controlled by the pump inverter, which is controlled by the determine the heat transfer load of a cubic building surrounded by walls as shown in the drawing. The pressure bypass the thickness of the wall can be controlled. In order, if the pressure is beyond the set value, 100 millimeters, the number of rotations of the pump motor is glass with insulation material. The pump has a minimum motor rotation number to secure a minimum flow rate. This building has if the pressure increases while the pump motor is rotating, the overall heat transfer coefficient is 0.69 watts per Kelvin per pressure control valve PCV1. The total area of all the walls is flow rate of the pressure control valve used if the room temperature is 26 degrees Celsius while the outdoor temperature is minus 4 degrees Celsius. The heat transfer load of the construction framework is 124 watt capacity of the pump. If the pressure load can be reduced with the use of a material having a low thermal conductivity or thicker member, reduce the initial cost. When the chilled water pump stops, the heat coming through glass windows into the room is divided into the heat directly penetrating the glass. The heat carried into the room by convection and heat radiation after the glass was warmed following through absorption into the glass, and the conduction heat caused by the temperature difference between the inside and the outside of the room operated full capacity. I have already explained the heat of transmission caused by the temperature difference between the inside and the outside of the room. Supply water pressure cannot be controlled. I will explain how to calculate the load caused by the heat directly penetrating glass and the load caused by solar radiation. Operation mode multiply the area of the window by the solar radiation heat load to the window and the shading coefficient operating brine chiller using the conditions shown in the drawing. Closing of the switching valves and control valves for the brine pipeline. The area of the window is 0.5 square meter. Temperature control is carried out as the standard storage gain of a window is 180 watts during the square meter. And direct chiller operation is transparent. A pump sends air into the ice of the glass is 3 millimeters. The ice around the two tri-colored window shapes are used. As select 0.6 the efficiency of the shading coefficient of the window area. You will get 59.4 watt of the solar load. Water pressure control during discharge and direct chiller operation. The people load is and some of the sensible heat load and the latent are the same as those carried out during discharge and the latent load are determined respectively by multiplying the people load cost per people by the number of people in space. The external melting the number of people in the room is often uncertain. Determine, therefore, the number by referring to the table. The external melt ice that the area of an office is 100 square meters while the room temperature is 20 degrees from the outside of the calculate the sensible heat and latent heat shown on this slide consists of an external melt ice on coil thermal storage tank, a brine chiller, a brine water heat exchanger, Hex 1. A brine pump,
An air pump to store the ice in the ice thermal storage tank. A water heat exchanger. Hex 2. A primary chilled water pump and a secondary chilled water pump. The automatic control system includes the following components. The temperature sensor TE3 to detect the temperature in the thermal storage tank. The water level sensors LE1 and LIC1 to detect the water level in the thermal storage tank. The system controller to turn on and off the brine chiller by thermal storage capacity. The switching valves TCV1 and TCV2 for the brine pipeline. The temperature control valves TCV5 and TCV6 for the brine pipeline. The switching valves TCV3 and TCV4 for the chilled water pipeline. The temperature control valves TCV7 and TCV8 for the chilled water pipeline. The temperature sensors TE1 and TE2 to control the temperature of chilled water at the outlet of the heat exchanger. The temperature indicating controllers TIC1 and TIC2. The pressure sensor PE1 to control supply water pressure of the chilled water pump. CP2 and the pressure indicating controller PIC1 and the pressure bypass valve PCV1. Operation of the external melt ice on coil thermal storage system will be explained. First, charging storage mode to generate ice by operating the brine chiller will be explained. During charging storage mode, opening and closing of the switching valves for the brine pipeline are switched as shown in the table on this slide. As a result, a closed circuit is formed by the brine chiller and tube pipe in the ice thermal storage tank. If the closed circuit is formed, the brine water heat exchanger is separated from the circuit. The primary chilled water pump, CP1, and the secondary chilled water pump, CP2, stop. The turning on and off of the brine chiller is controlled based on excess and efficiency obtained from comparison of the thermal storage capacity of the ice thermal storage tank and the target thermal storage capacity for the corresponding time of day. The thermal storage capacity is determined by calculating the temperature detected by the temperature sensor TE3 in the ice thermal storage tank and the water level detected by the water level sensor LE1. Next, discharge mode to melt ice and send chilled water to the secondary load side, air conditioner, will be explained. During discharge mode, the primary chilled water pump, CP1, and the secondary chilled water pump, CP2, operate to control the temperature of the chilled water at the outlet of the water heat exchanger. Opening and closing of the brine switching control valves and the chilled water switching valves are switched as shown in the table on this slide. As a result, the brine water heat exchanger is separated from the secondary chilled water pipeline. The brine chiller stops. The supply chilled water temperature during discharge mode is controlled based on the temperature TE2 of the outlet of the heat exchanger for chilled water and by the temperature indicating controller TIC2. Meanwhile, the amount of chilled water on the primary side is controlled by the temperature control valves TCV7 and TCV8 installed on the chilled water pipeline so that the temperature of the supply water can be maintained at the set value. In addition, during discharge mode, a stirring pump sends air into the ice thermal storage tank. The ice around the tube pipe is uniformly melted. As a result, the efficiency of radiation is enhanced. Next, supply chilled water pressure control will be explained. The supply water pressure on the discharge side of the secondary chilled water pump, CP2, is detected by the pressure sensor PE1. The number of revolutions of the pump impeller is controlled by the pump inverter controlled by the pressure indicating controller PIC1. In addition, the pressure bypass valve PCV1 is PI controlled. If the pressure is beyond the set value, the number of rotations of the pump motor is respectively reduced. The pump has a minimum motor rotation number to secure a minimum flow rate. If the pressure increases while the pump motor is rotating at the minimum rotation number, the pressure is controlled by opening the pressure control valve PCV1. The rated flow rate of the pressure control valve used under inverter control is often selected based on 30 to 40% of the rated capacity of the pump. If you select the rated flow rate of the pressure control valve based on the rated capacity of the pump, if the pressure is controlled by the pressure bypass valve, and if you cancel inverters, you may reduce the initial cost. When the chilled water pump stops, PI calculation by the pressure indicating controller PIC1 can be stopped. As a result, enhancement of integral control caused by the difference between the PV value and the setting value is prevented. If this calculation is carried out while the pump is stopped, the inverters operate at full capacity, and the pressure bypass valve remains completely closed for a while. As a result, supply water pressure cannot be controlled. Next, discharge and direct chiller operation mode will be explained. During discharge and direct chiller operation mode, ice is melted in the ice thermal storage tank, while the brine chiller parallelly operates with the brine water heat exchanger, forming a closed circuit between them. Discharge and direct chiller operation mode occurs when the thermal storage capacity is running out and cannot keep up with the chilled water loads. The supply chilled water temperature during discharge and direct chiller operation mode is controlled by the water heat exchanger, HEX 2. In addition, the temperature is controlled based on the supply water temperature TE1 of the chilled water at the outlet of the brine water heat exchanger, HEX 1, and by the temperature indicating controller so that the supply water temperature reaches its set temperature. The quantity of brine on the primary side is controlled by the temperature control valves TCV5 and TCV6 installed on the brine pipeline. In addition, during discharge and direct chiller operation mode, a pump sends air into the ice thermal storage tank. The ice around the tube pipe is uniformly melted. As a result, the efficiency of radiation is enhanced. Supply water pressure control during discharge and direct chiller operation mode, and actions carried out when the pump stops are the same as those carried out during discharge mode. This is the end of the explanation of automatic control of central systems, Part 3.